So today we are going to study a topic which is another aspect of statistical inference, and this is known as the testing of hypothesis. So hypothesis, this term, I hope you have heard in many contexts, but when we say statistical hypothesis, we need to maintain certain thing mathematically. So in general, hypothesis is a conjecture about maybe certain phenomena or certain population. In statistics, we mean by hypothesis, the word hypothesis, that it is stating some property of the population. And the property what we want to mention through hypothesis, that must be a measurable property. It will not be something which we will not be able to record. Statistically, it must be measurable. And the population for which we are stating the hypothesis, we should be able to collect samples from there. This is a fundamental aspect that we need to keep back in mind. Otherwise, evaluating the hypothesis or testing the hypothesis will not be possible. So say for example, if I state that average score of your section in this probability course will be, say, 67%. My statement might be correct, might be wrong. And not only that, if I take a sample of, say, 50 students, I may not be able to verify, justify my statement. But the sample you have taken, you may be able to justify the statement. So the statement, whatever given, that may or may not be justifiable with the sample that we have collected from the population. Now, the story doesn't end here. There are also another statement. If the first statement, what we have given, if that is not correct, then whether the second statement is correct. So it is not a standalone thing. There are two competing statements are given in hypothesis. One is known as the null hypothesis. Another is known as the alternative hypothesis. So precisely framing the statement of null hypothesis and alternative hypothesis, there is no hard and fast rule, but we prefer to make the statement of the null hypothesis and alternative hypothesis in such a way that we can verify the statement, whatever may be chosen as the null, in an easier way. So the definition theoretically is this, that the null hypothesis, usually written as H naught, that makes a subset in the parameter space, which is capital theta, and the subset specified by the null hypothesis is usually denoted by capital theta suffix 0 or not. An alternative hypothesis, which is denoted by capital theta suffix a, is another subset of the parameter space, the subset specified by the null hypothesis and the alternative hypothesis, they should be disjoint. This is the prime requirement. Whatever I am claiming in the null hypothesis and whatever I am claiming in the alternative hypothesis, there should not be any ambiguity. There should not be any common point. So precisely, null hypothesis specifies a subset in the parameter space. It may be singleton, it may not be singleton. Alternative hypothesis also specifies a subset in the parameter space. It may be singleton, it may not be singleton. And it is not a necessary requirement that the set specified by the null hypothesis and the set specified by the alternative hypothesis, their union will be the whole parameter space. That is not the necessary requirement. The necessary requirement is this, that the set specified by the null hypothesis and set specified by the alternative hypothesis, they should be disjoint. Okay. Now we derive a test rule, which is a statistical procedure based on the distribution of the test statistic, which will either reject the null hypothesis or it will not reject the null hypothesis. And when we reject the null hypothesis, we will go by the alternative. So the statement is given in this way, that we reject the null hypothesis in favor of the alternative. Okay. So this is the usual framework of null and alternative hypothesis. Any query? Hello.
Sir, in the definition of hypothesis, in the third line, it's written if theta A is a singleton set, should it be theta naught?
No. Okay. Yeah. Yes. This one should be theta. Yeah. Correct.
Okay. Thank you, sir.
Yeah. Then it is called simple null. And if theta A is a singleton, then it is called a simple alternative. Okay, so let us at least give one example here, that it's frozen. Meters. Wait. Yeah. Some lag is. Wow. Last day. Technical problem. Okay, chalo. I will, in the break time, I will restart it anyway. Coming? Yeah. Okay. No. Yeah, okay. Okay, so for example, if we say that the testing of hypothesis, testing of so say for example, if I state this, that H naught average Indian male has height 5 feet 6 inches. Alternative, average Indian male has height larger than 5 feet 6 inches. Okay. So this is simple null, but this is composite alternative. And here the set specified by the null hypothesis and the set specified by the alternative hypothesis, they doesn't consist of the whole parameter space. Whole parameter space can be larger than this. So it is only considering the 5 feet 6 inch and larger than 5 feet 6 inch. There can be the values less than 5 feet 6 inches. Okay. Second thing you can say, yes, please.
Sir, why is the above one simple null? Because it can contain more than one persons, right?
No. As specified by this statement, it is simple. This is specifying only one point, right? So in the real line, or okay, so let us consider from 0 to infinity. So it is somewhere 5 feet 6 inch. So the set specified, this is theta naught. Only this one.
Okay.
And for alternative, it is larger than 5 feet 6 inch. This part is not in the hypothesis. So, okay, so again, something similar, let us call that H naught is the average heat in a pop-up advertisement average rate of is say 0.23 and alternative is average rate of heat in a pop-up advertisement is not equals to 0.2. So here you can see that your rate, you can model it with Poisson lambda, and the null hypothesis is specifying H naught lambda equals to 0.23. Alternative hypothesis is specifying lambda not equals to 0.23, and you know lambda is greater than 0. So here null hypothesis and alternative hypothesis are complement of each other. So if you take their union, you will consist of the entire parameters. So this is simple null composite alternative, but their union is the whole parameter. Okay. Then another way you can have when both of them can be simple or both of them can be composite. So if I write in this way that H naught so the maximum power consumption is in a host in a household is say 10 units or less than 10 units or equal to 10 units per day, and H1 is saying that the maximum power consumption in a house is more than 10 units per day. Okay. So here both are composite, less than equals to 10 and greater than equals to 10. So 0 to 10, this is your specified by null hypothesis. 10 to infinity, this is specified by alternative. So their union is 10. For example, you can have both of them singleton. So H1 is the average rainfall in India, or maybe let us say KGP, how much is going on. Okay, whatever, maybe say 35 centimeter, and H naught, H1 is saying average rainfall in KGP. So both of them are singleton. So simple one, simple order. Now another kind of these are everything is well specified, but there are other possible alternatives. Hypotheses are there, it's like this that H naught, the score of probability statistics follows normal distribution alternative code of probability statistics course follows gamma distribution. So here the situation is little bit different than whatever you have seen so far. But still we have the testing tool by which we can perform. We will not do this thing in your course, but these are the hypotheses that we can also go for testing. Okay, any query?
Sir, how will you classify whether it is simple or composite?
Okay, simple or composite means?
The last one, the last example.
Okay, here both are composite because I am not specifying the parameter. It could, if I specify normal distribution, mean 50, variance 5, singleton, gamma distribution, alpha something, beta something, lambda something, it is composite. Here, the full family of normal is present there. Here, the full family of gamma is present. So, it is composite. Is it okay?
Yes.
So, this is the. Now, what happens? So, you have data from population that may be I mean finite population like your class or large population. That means you can take as n is going to infinity like the population of in India or theoretical population. That means you are a distribution specified, you can draw as many samples you want from that population. Okay. So data from populations are collected or given. Then hypothesis H0 and H1 are pre-specified. Now you have to go for the testing of hypothesis. So what may happen given the data, then you need to construct a test rule by which you will perform the test. So what could be your conclusion? That either H0, you go by H0 end of the day, or you go by H1 end of the day. Okay. And what could be the reality? The reality could be either H1 is true or H0 is true or H1 is true. So there are 2 cross 2 possibilities. H1 is true and you are going by H0 is true, you are going by H0. Or H1 is true, you are going by H1. But there are other possibilities also. H0 is true and you are rejecting H0. Or H1 is true and still you are going by H0. So these are the 4 cases that might happen. So here, this is an example. Here I can. Is it visible? This box.
Yes, sir.
So null is true or null is false. Fail to reject the null or reject them. So null is true, and I am not rejecting the null hypothesis given the data hypothesis specified and whatever test rule I have constant. So if null is true and we are not rejecting the null hypothesis, then we are going by the null hypothesis, then our decision is correct. Now, if the null is false and we are failing to reject the null hypothesis, then it is told, it is termed as the type 2 error. Why type 2 and why type 1 I will tell you later. But the terminology is when the null hypothesis is false and we fail to reject the null hypothesis, then we call it is a type 2 error. But if the null hypothesis is true and we reject the null hypothesis, then it is called as a type 1 error. And finally, if the null hypothesis is false and we reject the null hypothesis, this is also a correct decision. Well, the probability of that is known as the power. Now, let us go. So, first of all, we need a test rule to do or to take all these decisions. So, test rule is nothing but a test statistic and a decision-making number. If the value of test statistics is larger than this, I will go by null, or less than this, I will go by null, or in between this, I will go by null. So this kind of thing, very straightforward, a decision-making rule where how and when I will go by the null or by the alternative that is given by the test rule. But the test rule, interestingly, makes a partition in the sample. So say for example, if I say as an example that how we will come up with a test rule, that is a separate story, I will tell you. But say for example, if I specify the test rule in this way, that if say x bar is greater than 59, I will conclude, or I will go by the then go or reject H naught, which is specifying that mu equals to say 55, and if x bar is less than equals to 59, do not reject H naught, which is claiming mu equals to 55, and H1 is claiming that mu is greater than. Okay, so if x bar is greater than 59, I will reject H naught and I will go by H1. If x bar is less than or equals to 59, don't reject H naught. So you go by H naught, end of it. So if suppose somehow I have come up with this rule, now you see that this is the rule given the data. What does it mean? It means that x bar, I need to consider the region x bar greater than 59. That means sum over xi greater than n times 59. Okay. So this set is equivalent to this set. So here, if you consider S is the sample space, with this x1, x2, xn vector, then some of this vector will satisfy this condition and some of this vector will not satisfy this condition. Okay, so I can call that it is S naught, which is a subset of S that satisfies sum over xi greater than n times. So S naught is satisfying this condition.
Sir, in this case, the n is the number of elements in S naught or S?
No, n is the sample size. S is the sample space of all possible values of x1, x2, xn.
Yes, sir, but in the last you wrote S naught, which is a subset of S that satisfies summation of xi greater than n into 59.
Yes.
That.
So by this I am saying that this S is a collection of n component vectors.
Sir, I was asking, like, if S naught don't contain all elements, how can we write summation over all elements in S? I equal to.
Yes, that is why I am saying S is the collection of, say for example, suppose n is 2. Okay. 2 samples you have chosen. Now I am considering all those 2 component vectors. Maybe say 1.5, 3, 7, 5, 9. In this way, all possible 2 component vectors from a particular distribution, whatever may it be, all these possible vectors are in S. Is it okay? Now S naught is a subset of S such that S naught, if you take the values from S naught, then say x1 plus x2 will be greater than some 2 times certain number, say 2 times 3.1. So this element from S naught, it will not satisfy this condition, right? But this element will satisfy this condition. Is it okay?
Yes, sir.
This will not be in S naught, but this one and this one will be in S naught. Is it okay now?
Yes, sir.
So it is making a partition in the sample space. You can see that it is making it the law in such a way that there is a clear-cut if-else condition. If this, go by this, if else, go by this. So whenever there is a if-else condition, some of the elements of the sample space will satisfy the if condition, other part will satisfy the else condition. That is what, as simple as that. Now, there are a few more terminologies. This set, the rejection region or the critical region, is a subset C of Rn, what we call as a sample space S, or you can say S. Then subset C of Rn such that X belongs to C is equivalently Tx will be rejecting the null hypothesis. So Tx, you can consider that the test rule, like Tx equals to X bar. Based on that, you can conclude whether you will reject the null hypothesis or you will not reject the null hypothesis. So it is equivalent to making a partition in the sample space, and the subset, if X belongs to that subset and that leads to the rejection of null hypothesis, that subset is known as the rejection region or the critical region. Now, under H naught, if the probability of X belongs to the critical region is less than equals to alpha, then alpha is known as the level of the test, and if the equality attains, then it is known as the size of the test. So for your course, everything will be size. We will not go for level alpha. So you can consider this thing that under H naught, the probability of rejecting the null hypothesis is alpha. And this alpha is a pre-specified number. Now let me come back to this once again. That rejecting H naught, when H naught is true, that is considered to be a more harmful for the system compared to fail to reject the H naught when H naught is false. It has a similarity with the judiciary system, that you are not supposed to punish an innocent rather than leaving a criminal free. So punishing an innocent person is supposed to be considered more harmful for the society than leaving a criminal or who is originally committed some crime free. So similar way, the rejecting the null hypothesis when it is true is supposed to be more severe error. That's why it is called the type 1 error, and we don't want to commit such kind of error. So as a consequence, we put a threshold on alpha. So we don't let the value of alpha to be very high. Usually in practice, alpha is taken to be either 0.05 or 0.01 or 0.1 in this. And the other error, that means when the null hypothesis is false and we fail to reject that null hypothesis, that is known as the type 2 error. And probability of occurrence of type 2 error is given by beta, its complement, that when null hypothesis is false and null hypothesis is rejected, its probability is known as the power. And as in estimation process, you have seen that there are methods of evaluation of different estimator. Here in testing procedure, if you have more than one testing rules for the same set of data and or same set of population and same set of null and alternative hypothesis, if you have more than one testing rule, then you can compare these testing rules provided they have the same level or size with their power. So you need to compare the power function given they have same size or level under the same null and alternative hypothesis. Data are coming from the same population. So to evaluate more than one testing procedure, we need to check the power function. To control the type 1 error, we need to keep a threshold in probability of type 1 error, which is alpha. And probability of type 2 error and power function are just 1 minus of one another because they could consist of the complement of the events. So power function is a function that probability x belongs to the critical region and it maps from the parameter space of alternative hypothesis to 0 to 1. Because it is a probability, if you map to 0 to 1, there is nothing special about it. but it is evaluated for each of the value of the parameter which are in the alternative hypothesis. So the tests you can compare only when they have the same level or size. Otherwise, two tests are not comparable. So type 1 error and type 2 error we have defined. So here, say for example, if you go for testing a data set, and very simply you consider that you are testing the mean 0 or mean not equal to 0. And you have come up with the rule, if I will reject the null hypothesis mean 0 if the data or the mean value of the data is greater than 2. If that is your testing rule, then if the average value of the data falls in this part or this part in the red region, you will reject the null hypothesis. So absolute value of the sample mean is greater than 2. So it is either less than -2 or greater than +2. You reject the null hypothesis. But although the data may come from the true null hypothesis, there is a probability that it will be large. The mod value of the mean will be larger than 2, and you may reject the null hypothesis. You can compute its probability of the type 1 error. The type 1 error region is denoted by the red color here. Similarly, here you can see that the type 2 error. Type 2 error, when you are seeing that this black, this left side curve is the true curve, and the right side curve is the alternative curve. But you can see that the alternative curve or the alternative density is very close to the true density. So in that situation, probability of occurring a type 2 error is more. The red region, in this red shaded region, if the data, although coming from the alternative, you are not able to reject the null hypothesis and go by the alternative. So if the two densities are too close, your power will be less, or in other words, the probability of type 2 error will be more. So that is what it is depicted in this diagram. But here you can see that the alternative hypothesis, the specified the density by the alternative hypothesis is far away from the true density, which is with mean 0. So the probability of occurrence of type 2 error is very less, and as a consequence, power will be more. So here, this is a typical power curve. Say for example, I am trying to test that data are coming from mean 0 population. Assume that they are normally distributed. Then, or if the alternative hypothesis is that the mean not equals to 0, then typical power curve you will see like this U-shape. But if it is one-sided, mean 0, mean greater than 0, it will not be, this U-shape will not be there. You will get only 1/2 of them, either in the greater than side or in the left. So that is how the power curve will behave. So now let me just give you an example how I will come to this lemma later on. Now let us go for the construction of a test. Any query before we go for the construction of a test?
Sir, can you explain the power curve again?
Okay, let me just construct one. It will be easy for me to explain. Okay.
So power curve is simply the probability of
rejecting the null hypothesis when it is not true. So only the true parameter is under null hypothesis. Parameter specified is 0. And you are rejecting null hypothesis when it is true with probability alpha, that is maybe say 0.05 or 0.01. But when as you go away from 0, either in the positive side or in the negative side, you are gradually rejecting the null hypothesis with more and more probability. So this probability is gradually increasing and you are reaching 1 in the right hand side, and similar thing happens in the left hand side. Is it okay?
Yes, sir.
Hello?
Yes, sir, it is okay.
Okay, so now let us see. Well, I'm not going for a formal construction through Neyman-Pearson lemma. I will state it later on. But these few steps, given the course and syllabus of yours, you can, if you can follow, then you will be able to construct the null hypothesis, the test procedure. So first of all, what you need to do, that to perform a test, estimate the parameter for which you are doing the testing. Okay. Then estimate the unknown parameter, if any. Then construct the test statistic and obtain its value. Then obtain the exact or asymptotic distribution of the test statistic under the null hypothesis. Depending on the alternative hypothesis and level alpha, decide the cutoff value or the rejection condition, and then compare the observed value of the test statistic as obtained in step 4 and the cutoff value from step 5 and conclude for the test. So this is a very simple few steps. Let us do a testing and you will be able to understand what we are trying to do. Okay, so suppose the x1, x2, xn, they are IID random sample. I'm considering the simple most situation, normal, mu, and 1. Or maybe, okay, so sigma naught square. Sigma naught square is known. A simple most situation I'm trying to depict. Now, the null hypothesis specified mu equals to 0. Alternative hypothesis, mu not equal to 0. As simple as that. Suppose these are the data of some measurmental error. So it is very easy to have construct this kind of. Now, given the data, maybe say n equals to, let n also can be 50 observations you have, and all these are numeric values. So given data will be like this. Say x1, observed x1 is small x1 equal to say 1.5. Observed value of x2 equals to small x2, say 0.5. Observed value of x3 is small x3 equals to say minus 0.7. In this way, observed value of xn equals x50 equals to small x50. Let us say minus 0.1, something like that. So this will be the data available with you. This is the hypothesis given to you for testing. Now, what will you do? So let us go step by step. First, estimate the parameter for which you are doing the testing. Okay. So step 1. So mu hat equals to x bar, and get it from sample. Okay, whatever sample you have, you will get a numeric. Estimate the unknown parameters, if any. So here we don't have any unknown parameter, so I need not require anything. Construct the test statistic and obtain its value. Okay. So now when we are talking about construction of test statistic, we can, so it is eventually meaning that you need to do a pivoting. Step 3, what you need to know, that you need to study this thing, that x bar minus, let's say, mu divided by sigma naught root. So this is your test statistic. In any circumstances, it will follow normal 0, 1. So that is why it is the test statistic. The pivoting I have done. Whatever may it be, this statistic will follow normal 0. In general, starting from a population this, it will follow normal 0. Now, obtain the exact or asymptotic distribution of the test statistic. So here, step 4. Under the null hypothesis. Okay. So now, in step 4, root n x bar minus under null hypothesis. So under null hypothesis, this quantity this will follow normal 0, 1 under H. If H naught is not true, this will not follow under normal 0. This will follow normal 0, 1 under H naught, because I have replaced this mu by the parameter specified by H naught. Okay. Now,
Sir,
what is the step 5?
excuse me, sir.
Yes, please.
So Z will follow normal 0, 1 irrespective of mu, right? That is how we construct it.
Yeah, so in general, this is true. When your data are assumed to come from any normal mu sigma square. So in general, if you have this transformation, it is supposed to follow normal 0, 1. But you are replacing mu by the parameter specified by the null hypothesis. Now you cannot guarantee that it will follow normal distribution in any circumstances. It will follow normal 0, 1 in any circumstances. It will follow normal 0, 1 only when null hypothesis is true. That means the data are coming from the null hypothesis.
Is this the hypothesis from H0? Like this won't follow normal 0, 1 if H0 is not 0.
Which one? I didn't get this. Please say again.
So from step 3 to step 4, here
Yes.
we are taking mu equals 0 from the null hypothesis.
Yes.
So here are we stating that if mu is not 0, then it won't follow normal 0, 1.
Yes.
But
Yes.
from step 3, it will always follow normal 0, 1.
Because step 3, I am using the whatever may be the value of mu, the same value of mu is used here. But here, a particular value of mu is used here.
Okay. Yes.
Okay. Now, depending on the alternative hypothesis and level alpha, decide the cutoff value of the or the rejection condition. Okay. Now, you have to step 5. So, this test statistic is supposed to follow normal 0, 1. So again, the similar diagram as we have drawn yesterday. So this region, this is Z alpha by 2. This region is alpha. This is region is alpha by 2. This is minus Z alpha by 2. This region is 1 minus alpha. So we decide that we reject the null hypothesis given alpha, say 0.05. We reject the null hypothesis if this Z observed, absolute value of that, is greater than Z alpha by 2. That means if it is falling in the shaded region, I will reject the null hypothesis. If it is falling this shaded region, or if it is falling this shaded region, I will reject the null hypothesis. Otherwise, we will go by the alternative. Now, suppose you got, suppose last step, that compare the observed value of the test statistic from step 4 and the cutoff value. Cutoff value is Z alpha, this is cutoff value, and conclude the test. So, so suppose in this case that whatever data you have given, that X bar, suppose X bar you have got, say, 3.5. Okay, so from sample you have got 3.5. N is 50. Sigma known, you can consider sigma naught equals square equals to 4. Okay. So now can you tell me what will be the Z observed? Z observed is root 50 into X bar is 3.5 minus 0 divided by sigma naught is 2. So please tell me the value.
12.374.
12.374. And if alpha equals to 0.05, Z alpha by 2, how much? 1.96, right? Okay. So if this is the situation, Z observed absolute value is greater than Z alpha by 2. Hence, the statement is this. Given the data, we reject H naught in favor of H1 at level alpha. This is a formal statement of a conclusion of a test. That we reject the null hypothesis in favor of alternative H1 at level alpha. Okay. Alpha, whatever you have chosen. This is the data specified, this is the parameter specified, and this is what. So, any query, any doubt within this procedure?
Sir, here, how did we choose the test statistic? Z equal to.
Okay, so how did you choose the test statistic? Yeah, this is a very fundamental thing. And okay, so first of all, I told you that you first start with the best possible parameter estimation method that you know. You start from there. Okay, so you are looking for mean. So you estimate it with sample mean. Then, given the feature of the data, you try to get the try to get a transformation from this estimator such that the transformed distribution becomes free from parameter. And that will give you the test statistic plugging in the value of the parameter specified by the null. This is an informal way I am saying to you. There are formal ways which are known as the construction of a test. One of the way is by Neyman-Pearson lemma, which helps to get the simple null against simple alternative. There are other ways which is known as the maximum likelihood ratio test, monotone likelihood ratio test. So all there are testing procedure how to construct a test, and there are also methods to get most powerful tests. So these are topic of a formal inference course that we cannot get into here just now. So this much you can remember, that you need to start with an estimator of your parameter for which you are doing testing. Then you need to get a transformation in such a way that the distribution of this transformed variable becomes free from the parameter. And that will be able to helpful for construction of test statistic and when you will plug in the values of the parameter under each node to that expression. Is it okay?
So means the only variable that can remain is the one which is specified in the test, like H naught.
No, I say again, please.
So means here only mu is the one that we are changing, like
Yes,
X naught
yes,
states
yes.
that
Because hypothesis is specifying mu only.
Yes, sir. So apart from that, everything should be fixed.
Intact. Yes. Apart from that, all expressions should be carried forwarded except this.
Okay, sir.
Sir,
Yeah. Good.
if sigma naught square was unknown, then we have to substitute sigma naught by its estimate.
Yes. Let us do that.
Sir, here Z alpha by 2 should be 3.9, right?
Z alpha by 2?
Yes.
No. You check.
Here sigma naught is 2.
Sigma naught is nothing to do with Z alpha. I want this expression as a whole. Z alpha is the upper alpha value for normal 0, 1. It has nothing to do with sigma.
Yes, Z alpha by 2 is the value after which the probability is 0.025.
Yes.
Okay, sir, I will check again.
Yeah, you can check. In fact, in the long back, in the note when I have given the normal distribution, you check there. I have given it, or you just say Q norm 0.975. Yeah, you can see 1.96 approximately. Is it okay?
Here sigma is.
Yeah, it is by default it takes normal 0, 1.
Okay, sir, yes. I took sigma to be 2. Now it is fine if you take one.
you did not mess up with sigma when you are checking Z alpha. That is what I am trying to say. Whatever sigma business you have to do, you do it here. When you are going for Z alpha, you go for normal distribution with normal 0, 1 only.
Okay.
You don't take sigma there and don't do all those stuff. You take whatever sigma here, x bar here, n here, whatever you have to do, you do with the statistic. The distribution should be free from all those known unknown parameters. That is what I am trying to say. Okay, so now sigma unknown. Page number. Okay. So now I am going for sigma unknown in a more general setup and trying to write it down. Say for example. Okay, so here is an example. Okay, so 10 sample size, true mean 10.5, standard deviation 1.2. Trend samples are drawn. So here you can see that 10 observations that you have got. Unbiased estimate of mean is this. Unbiased estimate of variance is this. Now Z test, as we have seen that you are testing for mu equals to 10 versus mu not equals to 10 when sigma value is pre-specified. Then this is the value of Z statistic that we have computed and standard deviation specified. Then this you can conclude. Here I will later on I will talk about the p-value and the confidence interval construction we have seen. So now let us go for two sample test, or sorry, one sample also can be done when sigma unknown. So let us go step by step. So maybe this B, this case. So just let me, so x1, x2, xn, IID, normal mu sigma square, mu and sigma square both are unknown. Okay, now what you need to do, step one, first specify the null hypothesis H naught, say mu equals to mu naught. It can be any number given. Mu, I'm going by the similar way that, or maybe mu greater than mu. Let me go. Mu greater than. One cycle. H1. Okay. Now, step one, what you need to do. You have to estimate mu. You can estimate by x bar. Whatever data you have got, you can calculate that thing from there. Step two, if you have any unknown parameter, you have to estimate it. So sigma square hat is 1 upon n minus 1 sum over xi minus x bar whole square. Ironing from 1. Okay. Then step 3, what you need to do? Construct the test statistic and obtain its value. So test statistic I am constructing in this way, that t equals to root n x bar minus mu divided by this quantity 1 by n minus 1 sum over xi minus x bar whole square. This is the test statistic, and in any circumstance for normal mu sigma square. This will follow in general T distribution with n minus 1 degrees of freedom. Okay, in general. Now, step 4. Obtain the exact or asymptotic distribution of the test statistic under the null hypothesis. Now, under null hypothesis, let's say, or I am writing this. Here I am denoting this. Root n x bar minus mu naught divided by 1 upon n sum over xi minus x bar whole square, I running from 1 to n. This will follow T n minus 1 under h. Otherwise, it will not follow. So now you obtain the value of the observed test statistic. Step 5. Step 5. Depending on the alternative hypothesis and the level alpha, depending on the alternative hypothesis and level alpha, decide the cutoff value or the rejection condition. Again, you do the same job. Here is the T distribution with n minus 1 degrees of freedom. So this is one-sided now. So I need to take for larger value. Alternative is saying mu is greater than mu naught. So for larger value, I will reject the null hypothesis. This region is alpha. This is tau alpha n minus 1. So reject H naught in favor of H1 if T observed is greater than tau alpha n minus 1 at level of. Now, step 6 is the final step. T observed, from data you compute whatever the thing, you plug in the value of say n equals to 50, square root that, x bar is 3.5, mu naught. Okay, you can consider some other number, maybe say mu naught, say 3. Sigma square hat, let us say x bar is 3.5. Sigma square hat, maybe say 4.5 estimated. So square root of 4.5. So now can you please tell me what will be the value? Root 50, 3.5 minus 3 divided by square root of 4.5.
5 by 3.
Say again.
5 by 3.
5 by 3. Okay. 5 by 3. So 1.66. Okay. And tau alpha n minus 1. tau alpha n minus 1. How much? Qt probability 0.95, degree of freedom 49. Oh wow, this is so marginal. You can see I have just somehow put those values. Now you tell me whether will you reject the null hypothesis or you will not reject the null hypothesis.
Don't reject, sir.
Reject or not reject?
So T observed is less than T alpha n minus 1, so we should not reject.
We should not reject. Yes. So this is 1.66 is whatever this, and tau. This quantity is 1.676551. Okay. So our conclusion is that given the data, we cannot reject H0 in favor of H1 at level up. This is the conclusion. Usually we don't write, we accept. This is the formal statement given that we cannot reject the null hypothesis in favor of the alternative. We usually don't write that we accept the null hypothesis. So that means it is again from that judiciary system that someone is, this is found not guilty type of thing. So that doesn't mean that guy is innocent. It is found not guilty. Just convention. So is it clear? Parameter known case, parameter unknown case. So now will you be able to do this thing?
Sir, what value of alpha did you take for this?
Alpha taken 0.05.
Okay.
Yeah, 0.95. So it is alpha is 0.05. Okay, so now will you be able to do this one? Sigma square equals to sigma naught square versus sigma square not equal to sigma naught square. This will be a chi-square test. Well, here I can tell you the way p values can be used. So most of the software, instead of doing this transformation and comparing in this way, they use p-value. So what is p-value? Suppose this is your test condition, right? This is the test condition or test rule by which you are rejecting the, you are going to reject the null hypothesis. Now, the situation here is this, that the test rule is saying that if the observed value of the test statistic is larger than this cutoff, you will reject the null hypothesis. Alternatively, what you can say that, so T observed, suppose here is your T observed. Here is your T observed. Now, according to the test rule, which is from this alternative hypothesis, it is coming as an upper tail test. So for higher value, you will reject the null hypothesis. So calculate probability T, which is following Tn minus 1 degrees of freedom, T greater than T observed. So eventually you are mimicking the test condition, but calculating the probability of the test statistic, which is under H0 following Tn minus 1. And now it is the observed value is there, but under the same null distribution, you are computing. So under H0, you are computing that the test statistic will have value larger than this, and larger than this or less than this, that is coming from your test rule, that you are going to reject the null hypothesis for higher value. Now this value is known as the p-value. Now you try to see that if the observed value is here, and if you integrate from this point up to infinity, whether this value will be greater than alpha or less than alpha.
Less than. Oh.
If this observed value of t is larger than tau alpha, and you integrate or you calculate the probability t greater than t observed, this value will be
Less than alpha.
less than alpha, right?
Yes, sir.
So this value, so it is equivalent that t observed is greater than tau alpha is equivalent that p value is less than tau alpha, and equivalent reject H0. And the other way also, if so, this is one case, t observed is, so if your t observed is here,
so p value should be less than alpha, not t alpha.
Sorry, t value is, thank you. T observed is less than tau alpha, that is equivalent to p value is larger than alpha, and that is equivalent to do not reject H. So usually software provides you the p value, and then you have more flexibility that instead of specifying alpha in beforehand, you can go by choosing alpha at the end of the test. So you will find that suppose your p value suppose your p value observed p value from the software, whatever, say 0.056. Okay. So whatever may be the test and whatever may be the test condition, you have software has taken care all of them, both sided, one sided, whatever may be upper tail, lower tail, all those things. After considering all those things, software has given you the p-value is 0.056. Now you have the flexibility that if you choose, say, alpha 1 as 0.01, then definitely you will reject H0. If you choose alpha, other choice of alpha 0.05, you also need to reject H0. But if you choose alpha equals to 0.1, you do not reject H0. So at size alpha 1, at size alpha 2, but here don't reject H0 at size or level, whatever, alpha. So it is important that what level of size you are choosing. P-value will remain unchanged, but depending on your level of size, you will either reject the null hypothesis or not reject the null hypothesis. This flexibility will be with you till the end of the computation. So in software, most of the cases, they will provide you the p-values. So here you can see that the p-value is very high. So there is no reason to reject them now. Here also p-value is very high. We are not going to reject the null. Here this is the test, chi-square test. P-value, you can see it is very low. 0.006984. So the null hypothesis is claiming that sigma equals to 1, or sigma equals to sigma naught, and here H naught is claiming that sigma square equals to 1 versus H1 sigma square not equals to 1. So software has taken care all of them, and they come up with the p-value 0.006984. As a consequence, we are rejecting the null hypothesis in favor of the alternative. And you can see that it is 2.7. It is a very high. Now, well, we have time.
Sir?
Yes, Bolo.
What will we do if it is very close, like 0.055, 0.057?
Yes, that is, well, that is a very interesting question. Thank you very much for this question. If it is really very close, then it is always recommendable that you draw another sample. In practice, it is always recommendable. In theory or in exam paper, you are given the data, whatever comes you do. But in practice, if you go very, very close to the either the cutoff value or like this one that we have just done, if you are really close, it is recommendable. Say for example, here it is must recommendable that that redraw the sample. Redraw the sample and perform test once again. Yeah, this is recommendation because this value is very, very close to the this one. This is always recommendable that you draw another sample means another chunk, 50 observations. This is okay. So now we can extend our ideas a little bit more. Here, this is a nice page. you will get all possible different ways of testing for testing rules, their cutoff value, their cutoff region, everything. This page has given everything very nicely. You can follow it. Okay, so tell me, which one should I start with? All of these are very much interesting problem and useful problem. Okay, so let us start with this Bernoulli because it is something different. X1, X2, Xn following Bernoulli P, perform the test H0 to check whether it is a biased coin or unbiased coin. Okay. So here I'm the size how much? Okay, so here also one real life example I had. For T, so here you can see that the machine that produces these pellets is a set of the pellets that are average 25 pounds. So they are willing to test mu equals to 25. Observed value of X bar is 25.51 from this sample. Sigma estimated is 2.193. Sample size n equals to 20. So the same construction that we have done, they have done, and they come up with the observed value of the T statistic is 1.04. Now they are doing a both-sided test because 25 pound or not equals to 25 pound. So they have taken alpha by 2 is 0.025. So the cutoff value is 0.2093 and the observed value is 1.04. So here is the observed value, here is the cutoff value. So they have rejected the null. So this is a very rudimentary example. We have done all the theory, but with nice diagram. So this is how. In exam, if it comes, then either you will be supplied with these all estimated parameter values or maybe some data, and from there you have to compute the test statistic and you need to conclude from there. Okay. So 165. So 165. So X1, X2, Xn are IID, Bernoulli, P, right? H0 is claiming P equals to 0.5, H1, P not equals to 0. Now here you see that you can estimate P by X bar, which is 1 upon n sum over Xi. Now, how will you do the standardization and how will you get it? The thing is, you don't know the small sample distribution. You can go for large sample test, which you can derive from CLT. So as a consequence, you know that X bar minus P divided by P into 1 minus P root n. Yes. This will converge in distribution to normal 0, 1 as n goes to infinity. Okay. So now the test statistic is say root n times x bar minus 0.5. Here there are okay, so let us go by this, that 0.5 into 0.5. So this is supposed to follow normal 0, 1 as n goes to infinity. So again, reject h naught in favor of h1 if absolute value of z observed is greater than z alpha by 2 at level. So suppose your observed value of x bar, so let n equals to 100, x bar equals to say 0.55, and what else? That's it. Tell me what will be the z observed. So root n is 10. This difference is 0.05 divided by 0.5. So it is 1, right?
Yes, sir.
And is it greater than z alpha by 2? Okay, now. So this is less than z alpha by 2. Okay? Do not reject h naught. Or again, given the data,
So we assume n to be reaching infinity.
yes, n is given 100. But we cannot reject h naught in favor of h1 at level alpha equals to 0. That's it. Similarly, for Poinsot distribution, that the example I have given, that the rate of hitting a random pop-up advertisement, you can model it with Poinsot distribution and you can do a test for lambda. There also you need to take care of large sample. Now let us see other problem. This one, let us go 164. And here, when you do large sample, there is a confusion always. People always say that, well, if you take more than 35 observations, it will be a large sample. That is a completely nonsense. Depending on the asymmetry of the distribution and stability of the variance, the large, how many samples will be the large sample, that varies. So if you start with very skewed distribution, taking it to the symmetric normal, it requires more sample size than a symmetric distribution with finite variance and standard. So if you are really in practice, you need to check that how much sample you require. There are sample size calculation procedure for normal distribution. If you are really interested, you go and read that. But that only sticking to that thumb rule 35 observation is good enough, that is not at all correct method. Many practitioner, many instructor, professor do that. I will strongly recommend don't follow that. You simulate and see how much samples you require for having a large sample distribution. If you have a provision, you collect that much sample and then you use the large sample distribution. That is my recommendation. At this stage, whatever theory you have done, you can do that. So you always remember that just crossing 35 observation or 40 observation is not good enough. Okay. Now, this is an interesting problem that xi, yi, you have paired observation. So if you have a paired observation and you are interested to know that whether the mean are same or not. So if I want to say that the length of your left palm and the right palm, whether they are same or maybe your score in math 1 and math 2, average score of math 1 and math 2, they are same or not. So for each individual, there are paired observations. Okay. Nothing specified. Just the hypothesis is saying the both observation has the same x component and y component has the same mean. Okay. Now, it is not specified what is the mean of x1, x, or what is the mean of y. Variance of x and what is the variance of y. It is also not specified what will be the correlation between x and y. So they can be different. So under the assumption that they have jointly normally distributed, that means bivariate normal distribution, you can construct a test which is known as the paired t-test. Okay. So it is very simple application, whatever we have learned so far. So let us see that xi, yi jointly follows normal, so normal 2 or bivariate normal, mu x, mu y, sigma x squared, sigma y squared, rho. And null hypothesis is claiming mu x equals to mu y, h1 mu x not equals to mu y. So as you can see that we can rewrite the null hypothesis in this way, that mu x minus mu y equals to 0, h1 mu x minus mu y not equal. As simple as that. So given this black hypothesis, let us define di, which is xi minus y. So expectation of di equals to mu x minus mu y. I can call it mu d. So this hypothesis is equivalent to saying h naught mu d equals to 0, h1 mu d not equals to 0. Already we have done this test. Is it okay? So di's are following. So let di's are following normal mu d sigma d square. Okay, whatever may be sigma d square. I don't care about it. So mu d hat is 1 upon n sum over di. Sigma d square is 1 upon n minus 1 sum over di minus d bar So that is called d bar whole square I running from 1 to n. Okay. So the t statistic is d bar minus 0 root n times square root of 1 by n minus 1 sum over di minus d bar whole square I running from. This is supposed to follow t distribution with n minus 1 degrees of freedom. And the test rule is reject H0 in favor of H1 at level alpha if T observed absolute value is greater than tau alpha by 2 in minus 1. That's it, as simple as that. Nothing special about it. Only rewriting the hypothesis is important. Okay. So now you can go for this other testing like two sample test. You can have different observations. How to do that? If interested, you look in this page, and also the ratio of sigma. That also you can do. You can check in this page, or everything are down there. So now let me just touch a little bit about this. Okay, so power. So now here you can so power curve, as we have told that we. So suppose this is the situation H0 mu equals to mu naught, maybe say 0, H1 mu naught equals to mu naught, which is 0. Now, so what your power is probability reject H0 under H1. Okay. So H0 is specifying only 0. Rest of the thing are under H1. So probability reject H0. That means probability x minus or x bar minus 0 divided by sigma naught. Let us say sigma known, or if it is not, you can go by t, no problem. This quantity is greater than z alpha by this quantity is greater than this under H1. Under H1 means in general you need to pick up all of the different values of mu, and for that you need to calculate this. Now if you by force if you consider H0, then this quantity is nothing but the level, and that will be alpha. Now as you will be gradually moving away from H0, that means original data you are now drawing from H1. So if the mean is say 0.1, then it has a little higher probability to reject. If it is 0.2, it has even higher probability. If it is 0.3, it is even higher probability to reject. And gradually it will go and stable it to 1. And similarly, if the mean is say minus 0.1, minus 0.2, so gradually this side also it is increasing because absolute value is there, and gradually you will go and you will stabilize. So that is how when the data, the mean of the data from where it is coming, that is deviating from the null, you will get more and more power. This is how it is. And finally, so let us come to this Neyman-Pearson lemma. So Neyman-Pearson lemma, what does it say? It is a precise method for obtaining the most powerful test, and it is given by the Neyman and Karl Pearson that to test H0, simple null, theta equals to theta naught versus H1, theta equals to theta 1. Theta naught and theta 1 are two distinct points. then reject H0 in favor of H1 at level alpha if this ratio, so you will write down the joint density of X for theta naught divided by the joint density of X at theta 1, if that entire quantity is less than some number xi, such that that means this is your rejection condition. If this ratio will be less than something, I will reject the null hypothesis. And to maintain the level of the size, under H0, here H0 is a singleton. So this ratio of likelihood, or maybe say density, that quantity less than xi equals to alpha. So you need to compute the value of xi from this condition. And that thing, if you derive, you will again come with this, say for example, if you are doing test for mu, sigma known, then you will come to that same conclusion that the xi will be z alpha by 2. If you, or maybe say if it is greater, mu1 is greater than mu naught, so xi will be z alpha. If mu1 is less than mu naught, you will come, xi will be minus z alpha. So in that way, eventually you will be able to extract the value of xi and the condition that if this quantity less than xi, equivalently x bar is greater than something or less than something, in that way it will come up. But that procedure I am not going for in your course. You can simply follow this step. You look at the null distribution of the test statistic and see what is the demand of alternative hypothesis, whether it is claiming you in the upper hand side, or it is claiming you in the lower hand side, or it is claiming in the both end. So decide accordingly what will be your rejection region, and you perform the test. I think with this note, I can conclude. If you have any query, please let me know. I'll be happy to answer. And
Sir, I have a doubt.
Yes, please.
Sir, it's not related to this. Sir, I'm just saying that if X and Y are two variables that follow normal distribution but are not independent, then will X plus Y and X minus Y, will these always follow normal?
Yes. Yes. Even it doesn't matter. So this is the unique property of normality. I don't know whether I have told you or not. That if okay, so sum over ai xi, I running from 1 to n, follows normal. So if and only xi's are normal. So it doesn't matter. If xi's are normally distributed, their linear combination will always follow normal distribution. And for any linear combination of x1, x2, xn, so this is for all a vector belongs to R. If for any linear combination of x1, x2, xn, if they follow normal, then individually each xi will follow normal. So this is a unique property of normal distribution. And even though they are dependent, it doesn't matter. Their linear combination will also follow normal.
Okay, sir.
And not only that, so say for example, you know bivariate normal, right? So if x1, x2 is following normal, say mu1, mu2, variance, covariance, so sigma 1 square, rho sigma 1, sigma 2, rho sigma 1, sigma 2, sigma 2 square. So this is the mean vector, this is the variance covariance matrix. Then A1, X1, A2, X2, you can immediately say that this will follow normal distribution with expectation of y and variance of y. And that thing you can easily compute in this way. Expectation of y is nothing but A1, A2, row vector, mu1, mu2 column vector dot product. So A1, mu1 plus A2, mu2, which is expectation of y. And variance of y is in this way, A1, A2, row vector. Then this variance covariance matrix, sigma 1 square, rho sigma 1, sigma 2, rho sigma 1, sigma 2, and sigma 2 square, then A1, A2 as a column vector. So you can, so row vector, matrix, column vector, then you can have A1 square, sigma 1 square, plus A2 square, sigma 2 square, plus 2 times A1, A2, rho, sigma 1, sigma. It is very easy to see, and that is variance. And this thing can be in general extended for n component normal distribution. So then it will be n component A vector. It is A transpose. So if I say it is normal mu vector V matrix, then the mean is A transpose mu. It is variance of expectation of y, and A transpose, or I can say this is sigma matrix, usually written as sigma matrix. So A transpose sigma A. This is row vector, this is sigma matrix, this is column vector, row vector, sigma matrix, column vector. So this quantity, if you write, then expand it, then it will be sum over AI, AJ, sigma ij in general, double summation I and j, and this is, you know, sum over AI. This is the general form of normal. Anything else?
Yes, sir.
So how was the overall experience of this course? Good, bad, ugly?
Yes, it was very good, sir.
Okay, thank you. So I hope this note that I have prepared and how we have developed. So always remember the approach. The same theoretical thing you will read in different books, but the way we have approached the subject, that is important, and those ideas that I have talked, how everything are connected, that will help you to, go deeper in any other subject, maybe statistics, maybe machine learning, maybe some other field. Investigating the reality, it will be helpful. So, okay, thank you. All the best for your final exam. Stay healthy and stay safe. Don't miss the exam. Hopefully everything will be fine. And follow the instruction, which whatever will be circulated through your MS Team and mail. So keep on checking your mails and MS Team regularly. Okay, so don't miss anything. Okay. The coordinator will circulate the instruction very soon, maybe tonight, regarding your exam. Follow that and prepare well. Thank you.
Thank you, sir.
Thank you,
Thank you,
sir.
sir. Thank you.
Thank you, sir.